Hello, I'm Leo Ferns with the Southern Nevada Water Authority, and I welcome you to the American Association of Water Distribution and Management's Thought Leadership Lab video module series. AAWD&M is a 501c3 nonprofit formed to advance the educational pursuits of water utilities and related entities throughout the U.S. There are a multitude of risks a water utility faces daily. According to the 2016 Water Research Foundation fact sheet, utility management enterprise resiliency, high hazard work, extreme weather, and advanced age of infrastructure are some of the most common water utility risks. This learning module series will focus on one of the risks, extreme weather, and how changing climate could affect water utilities' risk profile. Recent surveys of water utility staff suggest utilities are not yet prepared. In a 2017 American Water Works Association report, nearly half of the utilities reported that their utilities don't include any potential impacts from climate variability in risk management or in their planning processes. Water utility risk managers are now having conversations about climate, but not in the sense that changing risk from climate is integrated throughout risk management thinking. In contrast, water resource managers have made some progress towards integrating weather and climate impacts into decisions. This is the first of a three-part hour-long video module. The first module will be a brief review of risk types in the intersection of climate change with these risk types, followed by description of common risk mitigation strategies in the risk toolbox. The module will also describe what we know about weather and climate, why this should matter to risk managers, and what we should do to prepare for the future. The presenters for the first module are James Kirby, Risk Manager of the Southern Nevada Water Authority, and Jeff Lucas, Research Scientist with the Western Water Assessment Program at the University of Colorado. The second module will be a case study of how the Southern Nevada Water Authority and Denver Water have taken steps to adapt to risk associated with changing weather and climate. The presenters for the second module are Keely Brooks, Climate Change Policy Analyst for the Southern Nevada Water Authority, and Lorna Cates, Climate Scientist for Denver Water. The third and final module will be a discussion on how each sector currently deals with the exposure of changing climate conditions. James Kirby will rejoin us along with Rebecca Franco, Manager of Emergency Management for Denver Water, and Paul Fuller, CEO of Allied Public Risk.
A typical approach used by risk managers to categorize risk is to divide them into four quadrants. The most commonly used four quadrants are hazard, operational, financial, and strategic. Hazard risk arises from property, liability, or personnel loss exposures. Operational risk falls outside the hazard risk category and arises from people or a failure in processes, systems, or controls, including those involving information technology. Financial risk arise from the effect of market forces on financial assets or liabilities and include market risk, credit risk, liquidity risk, and price risk. And finally, strategic risk. This risk arises from trends in the economy and society, including changes in the economic, political, and competitive environments, as well as from demographic shifts. Extreme weather can impact any one of the four quadrants. Traditionally, risk management has only looked at extreme weather through the hazard quadrant. With extreme weather, such as flooding, windstorms, and wildfires, hazard risk typically results in property damage. Historically, risk management has managed the exposure of extreme weather hazard risk by transferring the risk to the insurance carrier. Depending on the insurance carrier's loss experience, the impact of these losses would be seen by the organization through premium increases. Unless the organization takes an enterprise approach to managing its risk, the risk management department typically would not get involved with mitigating the risk extreme weather can pose to the other three quadrants. From an operational hazard perspective, extreme weather can impact an organization's maintenance schedule. For instance, due to extreme heat, certain equipment may degrade more quickly and need to be replaced sooner than planned. Changing weather patterns could also impact maintenance schedules. Inconsistent precipitation could lead to inconsistent aquifer levels also. Financial risk resulting from extreme weather impacts the organization's liquidity. Extreme weather can expedite replacement of equipment and increase an organization's maintenance cycles. Utilities could experience increased capital costs associated with building new and rehabbing existing wells. Changing weather patterns can also have an impact on the cost to treat water. Changes in extreme weather undeniably impact the strategic risk profile of an organization. Based on the political environment, half of society may even question whether climate change exists. Depending on the environment of the organization, it may have to manage the risk of not offending its stakeholders while preparing for the potential consequences of changing weather patterns. Another huge strategic risk for utilities is the political environment and potential legislative changes. These regulations could be anything from impacting energy consumption decisions to impacting standards related to treating water. Risk managers need to understand the phenomenon of extreme weather and how to apply the appropriate tools to mitigate the impact to your organization. One thing is for certain, avoidance is not a viable strategy.
As James described, water utilities face risks from many different types of extreme weather: drought, heat waves, wildfires, heavy rain, river flooding and debris flows, storm surge and coastal flooding, snowstorms, extreme winds, lightning, tornadoes, hailstorms, and freeze events. What brings all of these together is the Earth's climate, which you can think of as the arena in which all weather, extreme or not, plays out. Weather is the always changing state of the atmosphere at short time scales, up to 1 week, while climate is the accumulation of weather over time, often expressed as averages. So we can also refer to the overall or aggregate risk from different extreme weather hazards as climate risk. We know that risks from extreme weather vary greatly across the country and from season to season. For example, floods are much more likely in the summer in the Rocky Mountains, but more likely in the winter in the Pacific Northwest. We also know that there are upward trends in many of these events over the past several decades across most or all of the country. First, the average temperatures have risen for most of the U.S. and extreme heat has become more frequent. There have been more frequent extreme precipitation events in most regions of the country. There have been more severe drought events, especially in the western states, and larger and more severe wildfires. And sea level rise is exacerbating coastal flooding. These trends are connected. A warmer atmosphere can hold more moisture, so when it does rain, the rains tend to be heavier. But in between rain events, a warmer atmosphere is a thirstier atmosphere, evaporating more moisture from the surface, leading to more severe drought and greater likelihood of large wildfires. And warmer temperatures cause melting of glaciers and ice sheets and also causes the seawater itself to expand, leading to sea level rise. For other events, such as tornadoes, hailstorms, and hurricanes, the long-term trends are less clear. The climate has changed throughout Earth's long history. What is different now is that the changes in climate are unusually rapid, and human activity is extremely likely to be the primary cause, mainly through increasing levels of greenhouse gases such as carbon dioxide or CO2. The concentration of carbon dioxide in the atmosphere, now over 405 parts per million, is about 1/3 higher than in 1960 and higher than at any time in the last 800,000 years. This means more heat is being trapped at and near the Earth's surface. This leads to warmer temperatures, which then leads to the changes in extreme weather. As long as the concentration of greenhouse gases in the atmosphere continues to increase, basic physics tells us to expect more warming. But how much? And how will the different types of extreme weather hazards change as more heat is added to the climate arena? To get a better handle on these questions, we turn to global climate models, often abbreviated as GCMs. Global climate models are complex computer simulations of the Earth's climate that incorporate physical theory, surface and satellite observations, and the collective scientific understanding of the most important processes that influence weather and climate. The models are not crystal balls, they're tools that show us plausible climate futures. We need to use the plural futures because each of the several dozen global climate models has a slightly different take on key processes and thus what the future climate will look like. Also, we don't know how future greenhouse gas emissions will play out. So we use different emission scenarios to represent that uncertainty. So rather than a single prediction of the future climate, like a forecast of tomorrow's weather, we end up with a range of projected climate conditions. If we look across the results from the different climate models, what we can say is that the recent upward trends in extreme weather are likely to continue. All of the climate models agree that average temperatures will continue to increase across the U.S. by 3 to 6 degrees Fahrenheit by mid-century, with the greatest warming in the interior West, upper Midwest, and Northeast. Everywhere, this warming will lead to more frequent and severe heat waves. And again, the warmer atmosphere will hold more moisture, leading to more frequent heavy precipitation and river flooding. Sea level rise is expected to continue and likely accelerate, so that by 2050, the U.S. coasts will see 4 to 18 inches of additional rise, and by 2100, a total of 1 to 6 feet, which will make coastal flooding from storms and high tides more frequent and severe. And dry spells are more likely to become severe droughts in the future, bringing more extreme wildfire behavior and increases in the overall area burned by wildfires. Warmer ocean temperatures will tend to make the most destructive hurricanes even stronger, though it's not clear how the overall number of hurricanes might change. And it is also unclear how tornadoes and hailstorms will change in the future. How annual precipitation might change in the future is much less certain than the average temperatures, but it is expected that the Northwest, Upper Midwest, and Northeast will see more precipitation on average, while the Southwest is expected to see less precipitation. Also, for those areas in the western and northern parts of the country in which much of the stream flow comes from snowmelt, that melt will occur earlier, by up to several weeks in a future warmer climate. And for a given amount of annual precipitation, the warmer temperatures mean that less of that rain and snow will be translated into runoff. So most areas of the country are likely to see changes in hydrology that will impact water supplies. To sum up, if we understand risk as likelihood times consequence, climate change is an overall risk enhancer or threat multiplier by increasing the likelihood of many types of extreme weather that impose costs on water utilities. These changes in likelihood are not just something in the distant future. They're happening now. This is why risk managers should care. The calculations of the frequency of damaging weather events that are used to assess costs and identify appropriate mitigation strategies are based on the historical record. Given the changing climate, these assumptions may not capture the actual hazard in 2018, let alone a few decades from now. Climate change may also drive emergent risks in which a threshold is exceeded, leading to consequences that had not occurred before. For example, warming beyond a certain point may lead to temperature exceedances for wastewater discharge in a system where that had never occurred previously. One could argue that the impacts of climate change are too uncertain to incorporate into risk management. And it is true that the science can't give you a single precise number, like that the inundation level of a 100-year flood event will increase by 22 inches by 2050. For that matter, it's difficult to pin down the historical risk for such rare extreme events. But the science can provide us with the direction of ongoing and future change for many types of extreme weather risk and sideboards on the likely amount of change. Water utility planning and risk management already considers other factors that are as uncertain as climate change, or more so, such as future population growth, per capita demand, economic growth, and local and state policy changes. As with these other risk drivers, changes in risk due to weather and climate can and should be assessed and managed, not ignored.